Something we'll often want to do for any vector space is find a spanning set for that vector space. And here's an example. So let's take this vector space of, this is actually a subspace of R3, of course, but the vector space of 3 entry vectors whose entries are parameterized like this. So to find a spanning set for this space, well, let's find a spanning set of linearly independent vectors, because one thing we've noticed in the past is that if you have linearly independent vectors, you can sort of treat that almost as like a coordinate system on the vector space. So let's come up with a linearly independent spanning set here. So every vector in this subspace looks like this, or has this form, and A and B can be any real number, right? Different choices of real numbers give us different vectors. But we can split this up in the way that we have become accustomed to, right? Based on what the free variables are. So we can split this up into 4A, 2A, 2B. Sorry, I need a 0 here. Plus, and then a vector that has the b's in it, minus 3b, b, and 2b. And then, of course, something to notice is that both of these vectors that we're adding here are in this vector space, right? Since we're looking for vectors that span this vector space, they have to be in this vector space. And then, in this first vector, every entry has an A in it, so we can write this first vector as 4, 2, 0 scalar product with A. And we can write this second vector as minus 3, 1, 2 scalar product with B, right? And of course, both of these are also in this vector space. So what this shows us is that every vector is a linear combination of these two vectors. And that means that these two vectors span this space. So we can write that this is equal to the span of 4, 2, 0 and minus 3, 1, 2. Now we are looking for a linearly independent collection of vectors. So now we have to ask ourselves, are these two linearly independent? Now in general, what we would have to do to answer that question is set up some sort of a linear system to check if one is to see if any vector in this collection is a linear combination of the others, or to see if there's some non-trivial linear dependence relationship. For this particular example, since we're in R3 and we only have 2 vectors, we can actually simplify this question, because if you're in any Euclidean space and you only have 2 vectors, they're linearly independent, or they're linearly dependent if and only if one is a multiple of the other. Right. If you have more than 2 vectors, things get more complicated, but with only 2 vectors, they're linearly independent as long as one is not a multiple of the other, and these two clearly are not multiples of each other, scalar multiples, I should say. So these are linearly independent. So this way that we've written this vector space as a span is actually with linearly independent vectors. And remember, having linearly independent vectors is kind of a nice way to write a vector space, because you can use linearly independent vectors as kind of a coordinate system, right? So just to make sure that this really accomplishes what we're hoping it's accomplished, let's just check. Suppose that we have a vector space spanned by some vectors, v1 through vk, and suppose that this vector space v is actually subspace in some larger vector space w. And let's further suppose that the v's are actually linearly independent. So let's ask ourselves, can we add or remove any vectors and still end up with a linearly independent set that spans V? I mean, it kind of seems like maybe we shouldn't be able to, but let's just check. Okay, so suppose, first of all, suppose we remove a vector. So suppose that we remove the last one, say. Okay, we need to ask ourselves two questions. Is this collection, I guess I should be using curly brackets here. If we throw away one of the vectors, is the resulting collection of vectors linearly independent? Well, the answer to that is yes. When we first talked about linear independence, we noticed that if you have a linearly independent set and you remove a vector, you get another linearly independent set. So now we need to check, does this set still span V? So does V1, I guess I can use curly brackets here. Does V1 through Vk minus 1 span V? And actually, we've already answered this question too when we talked about linear independence. The answer here is no. If you have a linearly independent set and you remove any one of those vectors, you will definitely change the span. So whatever V1 through Vk minus 1 spans, it can't be the same as V, because V1 through Vk were linearly independent to begin with. Okay, so can we remove any vectors and still end up with a linearly independent set that spans V? The answer is no. So for removing, no. So we can't remove any vectors. Okay, well how about if we add a vector? Can we add a vector and still add a vector to this collection V1 through Vk and still end up with a linearly independent set that spans V? Okay, well, there are two cases here. So let's take, to add a vector, we have to say what vector we're going to add. Maybe it's V. V is coming from our bigger ambient vector space W. There are two situations. The two situations are either little v is in big V or it's not. So if little v is in big V, right? Remember, big V is the span of V1 through Vk. So if little v is in big V, we can write little v as a linear combination, say A1, V1, up through, I should be writing pluses, A1, V1 plus dot, 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 AK, VK. And in this case, the collection of vectors V1 up through Vk together with V is clearly linearly dependent because this last vector is a linear combination of the ones that came before it. So that's a clear case of linear dependence. If you wanted to write down a non-trivial linear dependence relationship, you could just move V to the other side, and that would give you a non-trivial linear dependence relationship. Okay, so if this vector that we're adding is in V, then we can't keep linear independence, right? Okay, well, the other case is, what if V is not in big V? Well, if V is not in big V, then the span of V1 through Vk together with V, remember we're adding V, can't be big V, right? Remember, big V is the span of V1 through Vk. So how can we see that these aren't the same? Well, little v is in this one, clearly, because little v is in this spanning set, but little v isn't in capital V. Why not? Well, because we're checking the case when little v isn't in big V. So in this case, v1 through vk and v together don't span the same set, right? So can we add a vector and keep linear independence and have the same span? No. Either we lose linear independence or we change the span to something different than it used to be. So the answer to this one is also no, right? So what we're seeing here is that if you have a set that not only spans a vector space but is also linearly independent, that's sort of the best way to span that vector space. It's sort of, on the one hand, you can't remove any vectors. All of the vectors in this spanning set, you need them all, but also you can't add anything because you would either lose linear independence or change the span of the vectors. And for that reason, we give this kind of spanning set that also happens to be linearly independent a special name. We call it a basis. So if you have an ordered collection of vectors, v1 through vk, in a vector space V, then we call this collection a basis if V is spanned by those vectors and the collection of vectors is also linearly independent.